Welcome back to Fun Facts Online. Today we are turning our eyes upward, but not to the massive, iconic telescopes you might be expecting. When we think of astronomy, we usually picture the giants. We think of the Hubble Space Telescope, or the James Webb, or those massive white domes sitting atop lonely mountain peaks in Chile or Hawaii. These are what we call the era of big glass. For decades, the story of how we understand the universe has been written by these titans. They use massive mirrors, polished to atomic smoothness, to collect ancient photons with unmatched precision. They stare deep into the cosmos, looking at tiny patches of the sky to reveal galaxies billions of light years away. But there is a catch. These giants have a weakness. They are tunnel-visioned. To see the universe in such incredible detail, they must focus on a very specific, very tiny point. It is like looking at the world through a drinking straw. You see one thing perfectly, but you are completely oblivious to the fireworks erupting behind you. And that is a problem, because the universe is not a static painting. It is a violent, flashing, dynamic arena. Stars collapse in seconds. Neutron stars slam into each other, rippling the very fabric of spacetime. Black holes strip material from companion stars in sudden, lethal feasts. These events are called transients. They are the screamers of the universe. They do not wait for a scheduled observation time on the James Webb. They flash and fade, sometimes in mere milliseconds. To catch them, you do not need a giant eye that sees one thing perfectly. You need 1,000 unblinking eyes, watching everything at once. This brings us to the subject of today's deep dive, the BlackCAT Array. Launched on January 11, 2026, this mission represents a complete paradigm shift in how we do astrophysics. The BlackCAT, which stands for Black Hole Coated Aperture Telescope, is not a billion-dollar flagship. It is a CubeSat. It is a spacecraft roughly the size of a shoebox, specifically a 6U form factor, measuring just 10 by 20 by 30 centimeters. Yet, this tiny sentinel, built with the agility of a startup and the precision of a national laboratory, is poised to solve some of the biggest mysteries in cosmology. It acts as the tip of the spear for the global network of multi-messenger astronomy. To really understand why this little box is so important, we have to understand the prey it is hunting. The X-ray sky is nothing like the serene tapestry of stars we see with our naked eyes. If you could see in X-rays, meaning photons with energies thousands of times higher than visible light, the universe would look like a strobe-lit rave. The crown jewel of these high-energy transients is the gamma-ray burst, or GRB. These were actually discovered by accident in the late 1960s by the Vela satellites. Now, the Vela satellites were military spacecraft designed to detect nuclear bomb tests on Earth during the Cold War. Instead of finding nuclear tests, they found massive flashes of gamma radiation coming from deep space. GRBs are the most luminous electromagnetic events since the Big Bang. For a few brief seconds, a single GRB can outshine the rest of the universe combined. For a long time, these were a total mystery. Today, we know they come in two primary flavors, and BlackCAT is designed to hunt both. First, you have long GRBs. These last more than 2 seconds and are essentially the death cries of massive stars collapsing into black holes. Then, you have short GRBs. These last less than 2 seconds, and they are the result of a cosmic car crash, usually the merger of two neutron stars, or a neutron star and a black hole. These short bursts are particularly special because these mergers are the factories that create the universe's heavy metals, like gold and platinum. The game for hunting these bursts changed forever on August 17, 2017. That was the day the LIGO and Virgo gravitational wave detectors felt a tremor in spacetime. That signal was named GW170817. Just 2 seconds later, the Fermi satellite detected a short GRB from the same direction. Telescopes around the world swiveled to the spot and found a kilonova, the radioactive afterglow of the neutron star debris. This was the birth of multi-messenger astronomy. We were no longer just watching the universe with electromagnetic waves. We were listening to it with gravitational waves. But there is a massive bottleneck in this process. Gravitational wave detectors are like ears. They can hear a crash and tell you roughly where it came from, like saying it is over there on the left, but they have poor localization. They might narrow the source down to a patch of sky the size of 1,000 full moons. A traditional telescope like James Webb cannot scan that much sky quickly enough. It is simply too slow, and its field of view is too narrow. We need a wide-angle scout. We need a hunter that can watch a huge swath of the sky, detect the X-ray flash that accompanies the gravitational wave, and pinpoint it instantly so the big telescopes can follow up. That is the gap BlackCAT fills. But how do you shrink an X-ray observatory into a shoebox? X-ray telescopes usually require heavy mirrors and long focal lengths. The answer lies in a clever mix of retro technology and cutting-edge silicon. The team, led by Dr. Abe Falcone at Penn State, abandoned the idea of a standard lens entirely. Instead, they looked back to a technique rooted in the mid-20th century called coded aperture imaging. Let's try to visualize this. Imagine you are in a dark room with a single window. If you cover the window with a piece of cardboard that has a single pinhole in it, an image of the outside world will be projected onto the opposite wall. This is a pinhole camera. It works, but it is very dim because very little light gets through that one hole. Now imagine you punch thousands of holes in the cardboard in a very specific, complex pattern. The image on the wall will become a jumbled mess of overlapping shadows and light. To the human eye, it looks like noise, but if you know the exact pattern of the holes, the code, you can use a computer to mathematically untangle the mess. You can reconstruct the image of the outside world, but now it is thousands of times brighter because you let so much more light in. BlackCAT uses a mask made of tungsten or gold, which are dense materials that stop X-rays, perforated with a precise pattern of holes. This mask sits above the detectors. When an X-ray burst occurs, it casts a shadow of the mask onto the sensor. By analyzing the shift and shape of this shadow, the onboard computer can calculate exactly where in the sky the burst came from. The massive advantage here is the field of view. While a telescope like Chandra sees a fraction of a degree, BlackCAT watches a massive 0.85 steradians of the sky. It is a wide, unblinking stare ready to catch a transient event anywhere in its vision. But the mask is only half the battle. You need a sensor capable of recording that shadow. Traditional X-ray telescopes use CCDs, or charge-coupled devices, similar to the chip in an old camcorder. CCDs are great, but they are slow. They read out the image pixel by pixel, row by row. If the sky is bright or the burst is intense, a CCD can get piled up, meaning it gets bombarded by so many photons that it cannot count them accurately. BlackCAT debuts a revolutionary technology called the Speedster EXD. These are hybrid CMOS detectors. Unlike CCDs, where charge is dragged across the chip to be read, every single pixel in a CMOS sensor has its own amplifier. This makes them incredibly fast. But the Speedster goes a step further. It uses event-driven readout. Think of a standard CCD as a security guard who walks around a massive building, checking every single door, one by one, to see if it is unlocked. It takes time to do a full loop. The Speedster is like a modern security system where an unlocked door instantly triggers an alarm. The detector doesn't waste time reading empty black space. It only reads the pixels that get hit by an X-ray. This allows BlackCAT to react in microseconds. It can capture the rapid flickering of a black hole accretion disk or the millisecond pulses of a magnetar. It also saves power. CubeSats have limited battery life because their solar panels are small. By only reading active pixels, the Speedster sips power compared to the thirsty gulp of a CCD. Furthermore, the CMOS architecture is inherently more robust against the harsh radiation of space, which is a crucial trait for a mission operating in low Earth orbit. Speaking of orbit, let's look at the mission profile. BlackCAT launched on a SpaceX Falcon 9 as part of a rideshare mission. It was released into a sun-synchronous orbit at an altitude of approximately 550 kilometers. This orbit is strategic. A sun-synchronous orbit means the satellite rides the terminator, the line between day and night. This keeps its solar panels constantly bathed in sunlight for power, while allowing its instruments to point away from the sun into the deep dark of the cosmos. As it circles the Earth every 95 minutes, BlackCAT scans the sky. The onboard software is not just recording data, it is analyzing it in real time. This is edge computing in the vacuum of space. The satellite doesn't wait to download gigabytes of raw data to a ground station to ask humans if it saw something. It decides for itself. Here is the sequence of a kill. First, two neutron stars collide 130 million light-years away. A ripple of gravitational waves washes over Earth, triggering LIGO. Milliseconds later, a jet of high-energy particles drills through the debris, launching a beam of X-rays. That X-ray wavefront hits BlackCAT. The coded mask casts a shadow on the Speedster detectors. The pixels light up. Within seconds, the onboard processor notices the spike in activity. It compares the shadow pattern to its internal map and calculates the coordinates of the source to sub-arc-minute precision. BlackCAT cannot wait for a ground station pass. It powers up its low-latency transmitter, linking to a global relay network like the Iridium constellation. It sends a text message to Earth with the target coordinates and magnitude. This message hits the gamma-ray coordinates network. Within seconds, robotic telescopes on the ground and major space observatories slew to the coordinates. This entire sequence happens faster than you can explain it. In the old days, data analysis could take hours. BlackCAT does it in seconds. In the transient game, speed is everything, because the afterglow of a kilonova fades rapidly. If you miss the first hour, you miss the physics of the explosion. Now, while catching local neutron star mergers is the flashy goal, BlackCAT has a deeper, more ancient quarry, High redshift GRBs. Light travels at a finite speed, so looking far away is looking back in time. Astronomers use a metric called redshift, or Z, to denote distance and time. A redshift of 0 is here and now. A redshift of 6 or 7 takes us back to the epoch of reionization, the time less than 1 billion years after the Big Bang, when the very first stars were turning on. We know very little about these first stars, known as population 3 stars. They were likely massive, composed of pure hydrogen and helium, and they lived fast and died young. When they died, they likely produced massive gamma-ray bursts. Current GRB satellites operate in hard X-rays and gamma rays. While excellent, they sometimes miss the most distant bursts. This is because as the light from these ancient explosions travels through the expanding universe for 13 billion years, it gets stretched. A high-energy gamma-ray burst from the early universe arrives at Earth as a softer X-ray burst. BlackCAT is optimized for this soft X-ray band, specifically 0.5 to 20 keV. It is tuned to hear the whispers of the first stars. By detecting these high redshift GRBs, BlackCAT acts as a time machine. It illuminates the early universe, allowing us to answer fundamental questions. When did the first stars form? How massive were they? How did they enrich the universe with the first heavy elements? Each high redshift GRB detected by BlackCAT is a backlight that shines through the cosmic web, revealing the structure of the infant universe in silhouette. BlackCAT is also a statement about the future of space exploration. For decades, space science was risk-averse. The motto was often too big to fail, which meant billion-dollar budgets and decades-long development cycles. CubeSats like BlackCAT are the mosquito fleet of astronomy. They cost roughly $5 to $10 million, meaning you can build dozens of them for the price of one traditional observatory. They allow for novel technology. The Speedster EXD detectors might have been considered too experimental for a flagship mission, but on a CubeSat, they can be flight tested. If they work, they reach technology readiness level 9 and can be used on future giants. Finally, they offer scalability. The vision is not just one BlackCAT, but a litter of them. Imagine a constellation of 10 or 20 BlackCATs orbiting Earth, providing 100% coverage of the sky, 100% of the time. No transient could ever escape detection. Building a telescope in a shoebox is an engineering nightmare, of course. Thermal control is a major issue. In space, you cycle between boiling sunlight and freezing shadow every 45 minutes. Traditional telescopes use massive heaters and radiators to keep their optics stable. BlackCAT doesn't have the power budget for that. The team had to design a passive thermal system using advanced materials and flexures that allow the metal structure to expand and contract without warping the precise alignment of the coated mask and detectors. Then there is the data budget. The Speedster detectors generate megabytes of data per second, but the radio downlink can only handle kilobits. This is why the onboard AI is crucial. It must ruthlessly discard boring data, essentially background noise, and only save the interesting bits. It is an exercise in autonomous judgment. Despite the challenges, the future is bright. As BlackCAT settles into its commissioning phase, data is beginning to flow. The first light images confirm that the coated mask is casting sharp shadows, and the speedsters are clocking photons with nanosecond precision. But the real excitement lies in the unknown. Sometime soon, maybe tomorrow, maybe next month, a black hole will devour a star, or 2 neutron stars will dance their final waltz. A ripple will pass through the Earth. LIGO will trigger. And high above, a tiny box of aluminum and silicon built by students and dreamers will swivel its digital mind toward the flash. It will catch the light that has traveled for 1 billion years. It will send a ping to a server in Pennsylvania. And suddenly thousands of astronomers around the world will wake up, race to their control rooms, and turn their eyes to the patch of sky BlackCAT has marked. The BlackCAT Array is not just hunting high-energy bursts. It is hunting the answers to our origins. It is proof that in the vastness of space, you do not always need to be the biggest to make the greatest discovery. Sometimes, you just need to be fast, sharp, and wide awake. That wraps up our deep dive into the BlackCAT mission. Thanks for listening to G Fun Facts Online.